video. So in this one, we're gonna go over the second part of the problem in regards to conductivity, or not the second, but the second project. That's what I meant. And we're gonna go over problem one, the first problem, which deals about flow of a hot liquid inside a pipe, and then afterwards we're gonna go over the second problem. Okay, so for this first problem, we have that a hot liquid is flowing at a velocity of 2 meters per second through a metallic pipe having an inner diameter of 3.5 centimeters and a length of 20 meters. The temperature at the inlet of the pipe is 90 Celsius, and we have the following data. All right, and we are asked to find what is the convection coefficient in kilowatts per meter squared Celsius. So we are given the following. We have the density, we have the CP, right? Thermal coefficient. We have the viscosity mu, we have the thermal conductivity K, we have the length in meters, the diameter, we have to write that one in meters. And once again, we have the velocity 2 meters per second. So in order for us to find the convection coefficient, what we need to do is we need to find first, we need to use, you can see we have the Nusselt number, NU, that's the Nusselt number, which is equals to the convection coefficient times the diameter divided by the conductivity. So basically Nusselt, it's a way to relate conductivity and convection. But in order for us to find that H, we need to find the Nusselt, which is also a number that was found through an empirical formula, which is sometimes is, as you can see on the screen in green, it's 0.023 Reynolds to the 0.8 times the Prandtl number to the 0.33. And here we have the definitions for Reynolds and Prandtl. We have for Reynolds is the diameter times the velocity times density divided by the viscosity. And then for the Prandtl, it's just that Cp times mu divided by the conductivity K. So let's find that. Let's just plug it in and let's see what we get. So first we have to find the Reynolds and Prandtl that we need, right? So for Reynolds, if I put it, I will be diameter, which I do have here, which is 0.035 meters, times the velocity, which is 2 meters per second, times the density, which is 950 kilograms per meter cubed. Keep in mind that for Reynolds, it's a unitless number. All of these are unitless numbers, so all the units should cancel. And then divided by viscosity, which in this one is 2.55 times 10 to a negative 4 kilograms per meter times second. So we have meters, cube cancel, we have kilogram cancel, seconds cancel, that's good. And if we plug it in, our answer for our Reynolds number should be a pretty big number, which will be 26,000, or not 26,000, it's 260,784, which for a pipe, we know that the Reynolds number, anything about 2300, it's turbulent. So basically for this pipe, we know that this is pretty turbulent. But we'll use that for other calculations and different problems. All right, so let's find then the Prandtl number. So PR, it's equal to CP, which keep in mind, I was given it in kilojoules, but in order for this units to cancel, I need to write it in joules. So this should be 0.23 times 10 to the 3 joules per kilogram Celsius. And this is times my viscosity mu, which once again is 2.55 times 10 to the negative 4 kilograms per meter second divided by what's the K, which in this case is 0.685 watts per meter Celsius. All right, so if we plug this in, we should get our Prandtl number to be equals to 1.575. And now knowing this, we can plug it in for our Nusselt number. So NU will be 0.023 times 26784 to the 0.8 times our Prandtl, which is 1.575 to the 0.33, and we get Nusselt number to be 572, 575.2. Once again, all of these ones are unitless numbers. So then, knowing this, I'm able to find, I know that I can find h based from this definition. So according to this, h will be equals to my Nusselt number times my conductivity divided by my diameter, right? That's what that's what we basically should be getting. And after I plug in the numbers, I will get that this is equal to 575.2 times conductivity K, which is, what was it? 0.685 watts per meter Celsius over my diameter, which is 0.035 meters. And this will give me an answer of 11,257 watts per meter Celsius, but we want our answer in kilowatts. So if you multiply times or divide by 1,000, so in your code, keep that in mind, you have to divide by 1,000. We will have an H of 11.3 kilowatts per meter. Oh, and this should be meter square over here too. Meter square Celsius. All right, that should be our units, meter square Celsius. And this is our answer for this one. So you do the code, and this is pretty much what you should get. So for the second part of this project, we have the problem 2, which is something similar. But in this one, instead of flow inside the pipe, this is flow over a cylinder or over a pipe. So we have that the air is flowing at a velocity of 3 meters per second, perpendicular to a long pipe. We're not giving its length, but we're just saying that it's a really long pipe. The outside diameter of this pipe is 6 centimeters, and the temperature of the outside of the surface of this pipe is really hot. It's 100 Celsius. But the temperature of the air far from the tube, or basically the free stream velocity of the air, that temperature, it's 30 Celsius. We're given some data for these conditions. We have the kinematic viscosity instead of the other viscosity. So this one is nu, and this looks like a B, but it's nu. Nu, which is equal to 18 times 10 to a negative 6 meters squared per second. We have a thermal conductivity of 0.03 watts per meter Kelvin. We know the velocity, the diameter, the difference in temperatures. Once again, we need to find use the equations that we have here. They're asking us in this one to find what is our heat transfer per length. So we need to find the heat transfer through convection. We have the formula here, but you can see that in order for us, we need to find H. We need to do the same process again, where we find the Nusselt number. And in this one, for this setup, you can see the Nusselt number is something different. So once again, the Nusselt number will be something different depending on your setup. In this case, the flow is outside of the pipe, so the Nusselt number is just simpler. So let's start with the Reynolds once again. You can see that for this Reynolds is also more straightforward. We only have the diameter, which is 0.06 meters, times my velocity, which is 3 meters per second. And instead of multiplying times density and divided by the viscosity, I'm multiplying times the kinematic viscosity, nu, which is 18 times 10 to a negative 6 meters squared per second. And when you plug this in, you get your Reynolds number of around 10,000. So this is according to what we got from the code. Okay, so after that, let's find then the Nusselt number. So the Nusselt number will be equals to 0.024 times 10,000 to the 0.8. And when you basically plug this in, you should be able to use Nusselt number according to this should be 38. All right, we are rounding up some numbers. Maybe there's some decimals in there, but this is basically rounding up to simple numbers. All right, so from this, once again, we can find our h, and we know that h is equal to minus cell times k divided by diameter. So it will be 38 times k, which is 0.03 watts per meter Kelvin, divided by the diameter, which is 0.06 meters. And we're gonna get our h to be equals to, if we plug in everything, this one should be 19 watts per meter square Kelvin. And notice how this h is smaller because we have a smaller Nusselt number. So the bigger the Nusselt, you should have a bigger h. And this is basically the process that we use to find out what is the what's it called, the for convection, where is the constant, the heat transfer for convection in an empirical way. Okay, so we have this one. Now we need to find our Q per L, which we already have the formula. So Q per L is equals to H, which is in this case 19 watts per meter square Kelvin, times, in this case, the area of the cylinder is the outside surface area. That's why instead of being the cross-sectional, this is the area, like surface area, which is pi dl. But because we're divided by the length, and we know the length, we just multiply it times pi times diameter. I guess I forgot that one here. So pi d, and this will be d delta t. There we go. That seems better. So once again, we multiply times pi times the diameter, which we said is 0.06 meters, and this is times the basically the temperature difference, which we gonna have Ts minus T infinity. I'm gonna write them like this, but we know that one's 100 and the other one's 30. So when you plug this in, so we have 100 times minus 30, that's 70 times 0.06 times pi times 19. You should end up getting something around the range of, this will be 251 watts per meter. So let's just check. So we have meter, cancels with one of the meters. We end up with watts over Kelvin. This temperature will be in Kelvin or Celsius, same thing. And yep, we end up with watts per meter. And this is our heat transfer per unit length for this problem. All right, so once again, it's very straightforward. This one you don't require to plot anything. It was just us finding the heat transfer in different conditions. I believe this is similar to the ones you guys will be doing in the heat, what's it called? The flow over the cylinder, right? For your convection experiments. So you might be end up doing something similar to this. Of course, this is a simplification. The one you have, you take into account the radiation and whatnot, but it's a similar process that you guys will end up following. All right. Hope this was helpful, and I'll see you until next time.